One of the biggest expectations around quantum computers is that one day, quantum computers will train AI models significantly faster. And that begs the question, what is it about quantum computers that actually make this faster? Let's start with what goes into training a large language model and look at how quantum computers might disrupt the AI industry. Quick shout out to Sammy for helping me research this video. Let's start with an open model from Meta called Llama 3.1 from 2024. Llama 3.1 is a 405 billion parameter model that used 15 trillion tokens for pre-training, which means using just one GPU, it would take around 4,486 years just to train this model. And in order to reduce this insane number to something more tangible, we can simply throw more GPUs at the problem. Let's say 16,000 GPUs all dedicated to training this model, which brings the number down to 3 months as opposed to 4,000 years. In classical computers, we call this type of work parallel computing. And parallel computing is what enables us to train this massive model in such short amount of time by basically dividing up massive computational workload into smaller distributed tasks across hundreds of thousands of GPUs. So as you can see, if parallel computing in classical computers is undeniably effective at training AI models, what about quantum computers? How exactly does a quantum computer actually compare against parallel computing in classical computers? The reason why the Llama 3.1 model takes 4,486 years to train in the first place is because underneath most AI models that we train today, including modalities outside of LLMs, the underlying computation that needs to be done is this: matrix multiplication. Matrix multiplication refers to multiplying large grids of numbers together. And underneath neural network-based architectures, which is predominantly the case for all AI models now, the calculations that typically go into training are all done by multiplying many matrices of numbers. And these operations are measured in what's called floating point operations, or flops. And for the Llama 3.1 model, the total floating point operations to train the model require 10 to the power of 25 flops, which is a lot of calculations that need to be done. So that means in order for quantum computers to compete with classical computers, it needs to at least match in processing this unfathomable 10 to the power of 25 floating point operations somehow. So the natural question to ask here is this: if we have to do 10 to the power of 25 math operations in order to train this model, can't quantum computers just do all that math simultaneously like it was promised? And this line of thinking is actually very natural to think that way. I mean, after all, that's what we saw when we went from CPU to GPU. In other words, when we saw that CPUs have their upper limit in what it can do, companies like Nvidia stepped up and made GPUs to essentially outsource computationally heavy operations. So following the same trajectory, that might actually cause us to think for quantum computers the same way. And the line of thinking goes, okay, well, since CPU outsourced heavy computations to GPU, can't GPU then also outsource heavy computation to quantum computers, or QPU? The leap that we made from CPU to GPU works somewhat seamlessly given that they are both transistor-based architecture that processed information in a binary format, so carrying a bunch of zeros and ones through electrical signals. But the leap from GPU to QPU is a completely different game. In other words, both the CPU and the GPU store data in a deterministic way because the underlying architecture information is either a 0 or 1. But in quantum computing, they can be both 0 and 1 at the same time. So the leap that we need to make from going from GPU to QPU is going from a deterministic state of zeros and ones to now a probabilistic state where you have a varying probability of being a 0 while at the same time varying probability of being a 1. Which means if we wanted to outsource heavy computation from GPU to QPU, the tokens that are used to train AI models, which are stored in zeros and ones, need to somehow be encoded to a quantum state. But how? How do we actually take a deterministic state of information and encode it into a probabilistic state? One naive approach to this question might be this: well, if information that CPU and GPU use are stored in zeros and ones, can't you just store them in qubits in zeros and ones as well? In other words, if the data is 0 in a classical computers, can you just say 100% of 0 and a 0% of 1 and vice versa for data that is 1? Well, you certainly can do that, but if you are going to do that, why use quantum computers in the first place? In other words, why force quantum computers computers to think deterministically if the entire point of using quantum computers in the first place was leveraging the superposition where you have the phenomenon of having combinations of both states. Also, we just saw how effective parallel computing was, where it reduced a task that takes 4,486 years down to just 3 months. That to me is an indication that something is actually working pretty well. So the follow-up question to this might be this: what are quantum computers actually good for when it comes to AI? This is the question that top researchers and scientists are still trying to figure out, which is, where do quantum computers actually fit when it comes to AI innovation? Because competing against an already working method, which is parallel computing to train AI models, seems a little bit counterintuitive. And here's a good analogy going back to the transition from CPU to GPU. What I mean by that is that even though GPUs are clearly better than CPU when it comes to parallel tasks that require heavy computation, we actually still use CPUs for practically most things that we do on a daily basis, like browsing the internet, crunching numbers on Excel, and checking emails. We don't need to actually use GPUs for this, since they just work fine using a CPU. In the same way, this question emerges: do we really need to have quantum computers take on the burden of training AI models when parallel computing seems to be getting the job done fine? And this is exactly where a lot of skepticisms are being formed around where exactly quantum computers fit into the picture when it comes to AI. Are we aiming the gun at the right target and solving the right problem by trying to apply quantum computers for AI and machine learning? And this exact conundrum points to the harsh reality when it comes to quantum computing. If we want quantum computers to succeed, we need a market for quantum computers, because having a market creates incentives, and incentives drive innovation, investments, and competition. And one of the biggest markets that we have now is AI, which means there's excess capital flowing around the AI industry, which I covered in a separate video called AI Hype. And some amount of this excess capital could actually flow towards improving quantum computing as long as they work synergetically with GPUs rather than rendering them completely irrelevant. And Jensen Huang, the CEO of NVIDIA, said that NVIDIA will be a relic of the past, pointing to the true potential of quantum computers overtaking the GPU market in the same way how the GPU market completely overtook the CPU market over the decades. Jensen also sympathized with the harsh reality of quantum computing industry by reflecting back to when NVIDIA had to compete for funding when most R&D budget went towards CPU. But NVIDIA saw that there was a huge market with a low bar in the gaming industry, so NVIDIA leveraged the gaming industry to grow their footprint from there. And now, GPU is where all the public attention is going towards. NVIDIA is literally the most valuable company in the world, bigger than all the banks in the US and Canada all combined. And in the similar way to GPUs when it was trying to compete with CPU, investing in QPU or quantum computing seems a little bit risky despite its potential given its highly experimental nature. So this might lead you to wonder this question: if QPUs and quantum computers aren't providing anything meaningful to the society yet, why is there so much hype going towards the quantum computers? Is quantum computing just a nothing burger? The quantum computing industry has been in the race to scale over the past several years, but scaling here might not be actually what you think it is, at least in what we're used to seeing in the classical computing sense. In classical computing, scaling was largely guided by what's called Moore's law, which is an observation of how fast transistors on chips double every 2 years approximately. But in quantum computing, following the Moore's law would actually be a limiting factor, meaning Moore's law is actually not good enough. If you look at most frontier quantum labs in 2024, the number of qubits was in the hundreds qubits range. So following Moore's law, doubling every 2 years would put them only at less than 10,000 qubits by the year 2034. So yeah, Moore's law isn't going to cut it. So this leads to the next natural question. Okay, if frontier labs now have quantum computers with hundreds of qubits available right now, why can't we actually use that to train AI models today? While 100 qubits seems like it could do a lot, it's extremely common to have errors. And this error is more or less a feature in quantum computers rather than a bug. And for classical computers, errors are completely intolerable because we need things to be deterministic, either 0 or 1. But the probabilistic nature of qubits make it incredibly sensitive, and harnessing the quantum mechanics that power this also requires a completely different algorithm than what we saw in classical computing, and as well as quantum gates, which help us manipulate qubits in a more precise way. On top of that, companies like IonQ, Quantinuum, Alice and Bob, IBM, Rigetti, D-Wave, NVIDIA, and Microsoft, to name a few, are all trying to employ different hardware techniques like trapping ions, superconducting, annealing, all of which I encourage you to read more about what different approaches these companies are taking to overcome common roadblocks in quantum computers like coherence time, scalability, and gate fidelity. And as you can see, there's a lot to unpack here, but also a lot of potential for early adopters to take risks and innovate newer algorithms, newer gates, and newer methods of leveraging quantum state space in ways that we haven't imagined yet. So the ultimate question is, how will quantum computers actually pair up with AI? Do you think that quantum computers are better off focusing on a different industry other than AI? And will LLMs be something that we run on GPUs in the future, just like how we just run Excel on GPU? In other words, do LLMs solve a niche problem of processing language, just like how Excel solves a niche problem of processing numbers? Are we going to come up with a new way of harnessing knowledge that we couldn't even consider before with classic computers? What do you think?